Right, so let's move on to practical 2. So in this practical, we're going to look at a relatively simple technique, which is connected components labeling. But we're also going to look at a situation in which we attempt to use color in order to perform segmentation or to map an image from a color space into a binary image. Now, previously we've talked about doing this for a grayscale image. And in this example, we're going to be applying the concept to channels of a color image. And the image is crop peas on desk. And one of the things that I'd like to point out is that we're going to be looking at the original color space channel in red, green, blue, and considering where we might be able to set a threshold to separate peas from the background on this image. And we're going to find that by transforming the color space into normalized RGB space, we're able to do that, whereas the original color space doesn't allow us to easily do that. Okay, so this is an example of segmentation, if you like. We've really talked about it as going from an image to a binary image in chapter 2, but it really is a very simple example of image segmentation where you assign a label at a pixel level to indicate whether that pixel belongs to an object of interest or to background. So the things we're going to use, or the modules we're going to use, are scikit image. So the Python image library is one that you have encountered before. Scikit image is new. It's got some tools both for doing color space, excuse me, transformations, and also for doing image measurement and connected components labeling. So you should install scikit image, make sure that works okay, and please, if you are installing it, make sure that you're installing it in the same content environment as you're running your Jupyter notebook or Jupyter lab from. User documentation of scikit image is available online, and the documentation is pretty good. Okay, so these are the modules we're using. So from scikit image, we're going to begin by just using the color module, which gives us access to some color conversion routines. And here we're doing something we did, or similar to what we did in practical 1 on the color maps. We're loading an image from disk. In this case, the image is crop piece on desk. Note that this is held in a subdirectory called imgs. If you haven't downloaded this into that subdirectory, then you'd remove this subdirectory, imgs. Else you keep it in, or so you keep it in and just make sure that the image is actually in that subdirectory. So this returns image.open returns a Python image library object, which is a PIL object. So pimage is really an object that can show itself if you use matplotlib. So matplotlib knows how to work pretty well with this to display the image correctly. And this is what the image looks like. Now I can tell you that this is an RGB image, and so it doesn't have a color map, or there is no color map inside the file. So every pixel has red, green, and blue values stored. Okay, now we have previously looked at intensity-based segmentation in the lecture for chapter 2. So what we're going to do is to convert this image first of all into grayscale. So this command here maps the image from into a numpy array. Now it's possible that this SKCO RGB to gray would work without doing this mapping to a numpy array first. So I would suggest trying that, but in case it doesn't work in your version of matplotlib, then I would suggest doing this. So this NP array, what this does is so the image itself will have things stored in whatever format was closest to that on disk. In fact, the image may not actually be stored in memory. It may just be cached on disk. But let's see what this gives us when we after we've done NA. So if we do print type of NA, in fact, I'm not even sure we need to do print there. Let's just do that. Okay, so that's a numpy array. Let's just see what NA, if that works. Okay, so you can see it's an array. We can do np.shape NA, and you'll see that the size is 512 by 512 by 3. So we've got the 3 red, green, and blue channels stored independently. Okay. Now, once we've converted that to gray and displayed it, and I've turned interpolation, set interpolation to none here. In fact, I think that's an error. This should be none for reasons that we shall see later on. Then this is the image we get. Okay, so that's as close as can be to the original image. Now, what if we don't set interpolation? What happens is bilinear image interpolation is applied, and so you get a slightly smoother looking result. Okay, so we'll come on to that later on, and if we, when I've done this here, what I've done here is I've called skco.rgb to gray and applied that, call that on NA, and that returns a grayscale image. So the grayscale image, if we have a look at that and see what the structure is, or see what the shape is rather, GRIM, you'll see that that just has 512 by 512 elements. So it's a straightforward single plane array where the values in that array should refer to an intensity. And the range of intensities goes from 0 to 1. You can see that on the color bar here. This has not been displayed using a grayscale color map. So remember, and I've done this deliberately, that even though we've done this, which is to convert that to a grayscale image, that array, the way that array appears on screen depends on what color map we are using. So it's absolutely fundamental that we also then apply the correct color map to see this image correctly. So this is what the image should look like if we do this with a grayscale color map. So it looks like that. So this is a grayscale image displayed with a grayscale color map. So in pixel intensity displayed with a grayscale color map. Whereas here, this is pixel intensity displayed with a default matplotlib color map. So make sure you understand the difference between those, because it can be a bit confusing. And remember, we started off with an RGB image, so red, green, and blue, separate channels, and then did a color space conversion. Okay. Now you can see the P's here pretty easily based on the spatial structure. So we could use spatial structure to identify the location of the P's, but to do that, it helps to know what the average P looks like. And so this is one of the aims of this practical, is to get you to see how to create an average of a P by doing an ensemble averaging over examples of P's, which you could then use in order to, as a kind of template to find where P is located. So let's, we're not going to go into all of the template stuff in this practical. We're just going to deal with creating this average P. So let's see if we can set a threshold to detect this. So what I'm going to do here is to just see what values are present in the grayscale image. So get the min and max intensities. And so this is what I'm doing here. So as you can see, the values range from 0 up to a little bit less than 1. And we have floating point intensity values. So if we want to do a histogram of this, what we can do is say, let's use 100 bins and construct a histogram. Now, if we, in doing this, so saying bins equals 100, that tells the np.histogram routine how many bins should be created. And the bins are defined by their edges. So you've got the left edge and the right edge in intensity space. And within an intensity space, so not spatial space, but actually the possible values we have in the image, within that intensity space between 0 and 1, we're going to split that into 100 regions, so or 100 bins, so 100 intervals if you like. And the bin edges now tells us the left and right side, or the lower and upper value of each of those regions. Okay. And it turns out that there will be 101 bin edges. So we can see that if we just do this here. So if we do np.shape bin edges, we will see that we have 101 bin edges. So there's one more bin edge than there are bins in this histogram, which makes sense if you think about it. And to figure out the width of each of these bins, then we simply subtract any upper bin edge, any lower bin edge from any upper bin edge. That gives us the interval of the bin in terms of intensities that fall into that bin. So if we do that, we get we can specify that to be the width of the bars when we do our bar plot using plt.bar. We have 101 bins, and we have h will actually only contain, so let's have a look at that. So np.shape h. So we've only actually got 100 values of h, but 101 bin edges. And so what we do when we plot this is we specify that the x values, which is normally refers to along a histogram, you normally use either the bin edges to do that, or you use the center of the bin to define each location along this axis where the corresponding bar should be positioned. And so what I'm doing is just getting rid of the last rightmost bin edge, and then this align equals edge tells the bar plt.bar that instead of aligning the values in here along the horizontal axis, or the x-axis if you like, to be the centers of the bin, then what I'm specifying are the edges instead, which are present in this bin edges variable. H represents the height or the count in each bin. Okay, so that's the histogram of intensities. And the thing that you can see is that there is no really clear place of where you might put a threshold on this plot in order to separate the piece from the background, which is not surprising because if you look at this image up here, you'll see that although in general down here the P's have a higher intensity than the background, you'll see up here the background, because of this what's a specular reflection produced by a light shining on this desk, what's happened is that there's a very bright reflection from that area, and so in this area the P's will sometimes actually be darker than the background. If you make yourself aware of that, you can see it quite easily. Okay, this is just something about bin edges, which I've already explained. Okay, so now what we're doing here is we're going to the next bit, which is asks you to get the channels out of the Python image library object, which is pimage. And you may remember from the first practical that we can use get channel to do that. Now that should work without any problems, provided you've got the right version of the Python image library installed. So getting channel for red, green, and blue, and then displaying these. So in all cases, I've displayed these with a grayscale color map. And you remember we did an exercise on this for the lily image back in the practical for the first, or back in the first practical. So let's just do that here. So here are 3 color channel images, the raw color channel images displayed with grayscale. So we use grayscale because increasing values of intensity from black to white are correlated with bigger values in the channels, or the respective channels. So we can see that indeed the green channel does look like it has bigger values generally for the P regions, which is kind of expected. But as with the case of the lily image, there's a gotcha, which is that in this region here where we have very bright white reflection, so the color of that is quite white. Let's just scroll up here and remind ourselves of that. Okay, so this region here is quite white. So white is going to contain large quantities of red, green, and blue in equal quantity. And so the green P's against the white background will not give you that much contrast on the purely green channel. Indeed, let's come back down to this. We can see that on the green channel, there's very little difference between the interior of this P and that white background there. Indeed, in some of the P's, the value here seems a bit higher than that in the background. Sorry, lower than in the background. So that means that just the green channel isn't going to be great for this task. The blue channel looks a bit more promising if we were to take lower values of intensity as a potential way of setting a threshold. But you'll see there are some cases where that doesn't really hold very well, such as here. So we've got something that's much darker than the background and something that seems to be a little bit brighter than the background here on that blue channel. So even the blue channel isn't going to work in this case. So let's move on. The answer to this quiz, by the way, is that you can't set a threshold on red, green, and blue channels to separate P's from background. But it turns out that if you use normalized red, green, and blue, then this is actually achievable. So here we've got that done, and this is what the normalized red, normalized green, and normalized blue channels look like. Okay, here's the code for doing that. Important thing is to make sure that you take your red channel and turn that into floating point. Make sure it's floating point. So before doing any sort of calculation, arithmetic operation on pixel values, you should cast them into floating point types. Otherwise, your arithmetic may go wrong. And so I'm just using the calculation for red over red plus green plus blue, and this just avoids the divide by 0, and that's it. Okay, so there's normalized red, normalized green, normalized blue, and here are the channels for that. So you can see there isn't much information to separate P's from background on the red channel. The green channel is a lot more consistent now, and the blue channel also allows us to separate the P's from the background. And note that although there's still some variation in the color, the normalized blue in the P's, in individual P regions, in both cases, for example here, both of these cases we have on the blue channel that the P's are darker than the background. And you also note that almost magically, that reflection, the specular reflection that's present in the original image up here, that's present in the grayscale version of the image, and that's even present in all three of these channels here, is not present in the normalized channels here, which is another, it's a pretty spectacular validation of this this normalized red, green, and blue spaces. So hue, saturation, and variance, color space might also be similar, but this one, normalized red, normalized green, normalized blue, is so easy to calculate. Don't need any routines to do it. Just do the arithmetic yourself, and there you are. Right, so now we're going to look at setting a threshold on these channels to see what we can do. And so here we go with those three histograms. Now you can see that the normalized red doesn't have anything particularly interesting within it, as we've seen on the image itself. The normalized green gives us a clear valley between two peaks that we can use to set a threshold. Maybe not perfect, but it's a great start. And also normalized blue, we can set a threshold here. But we have to be careful with normalized blue because the P's in normalized blue correspond to the lower part of this, and the background corresponds to the upper part. So we have to, if we set a threshold, we take things below the threshold as belonging to object. That's for the blue channel. For the green channel, the P's are brighter or have higher intensity on the normalized green channel, and so you set a threshold and take everything above that. So you can do that, and it turns out that if you set this as your 0.37 or somewhere around there as your threshold, then you get a good binary mask. So this is the shape of that mask, and to visualize that mask, I think we do that somewhere. Yeah, we do that down here. So here's the image the binary image representing the p's using the default color map. Now note that on the left hand side we have a nice clean, cleanish result. On the right hand side the boundaries look a bit smoother, so you might prefer that, but if you look carefully you'll see that these boundaries actually have a green tinge around them. So that greenness comes from the fact that we're using that bilinear interpolation is being used by default in this image, and that's the default setting of matplotlib. The problem with that is that if you've got a binary image, it can create artifact because it tries to fit a surface to each of the three channels. It tries to fit a surface to your image array, and in this case what's happening is that in fitting that surface, it's in this case it's doing it on the red, green and blue channels. And so the problem there is that it's not doing the interpolation as intrinsically on the original grayscale values. The way it's working here is that it's mapping this into RGB color space and then doing the interpolation on each of those three channels, which is not the right thing to do, but that's what it does as default. Now you can turn it off using this syntax, which is very irregular, because normally the usual Python convention would be to do something like this, to say turn off interpolation, don't do any interpolation. But that actually fails to work and doesn't throw an error message. And so this is what you get as default behavior, and this is what we should get as what that mask looks like, or what that binary image looks like. Okay, so let's move forward. Right, the next step is to label each P. And to do that, what we're going to do is dive into the scikit image toolkit, and specifically the measure module. And from measure, we're going to import two functions, label and region props. So label is connected components labeling. So this is what PL will now be a connected components image, which is what you have here. Now, remember that to interpret this, the zero values still have a value of 0, but all of the P's that are distinct regions that are not connected to other P's are given one label, and that's what you're seeing here. And that's why they have a different color. Now that's not so easy to interpret here because we're losing some labels down here because their contrast with the background is not high enough. So scikit image has a routine for dealing with or producing better quality labels that are more visible. I shouldn't say better quality because they also have a slight issue. So this is a different visualization. I won't say better. And you can see that actually a lot of the P's now have unique labels. You can see the P's up here as well. But the coloring here is not good because this color is the same as this color. So this is not, this is what we have as a specialized routine to label things according to color, and it's not great. Or to visualize things according to color, and it's not great. So just be aware of the nature of the mapping from values in the image to whatever you see on screen. Okay, sometimes it's you need to think about it and really investigate the color map to see what's going on. But here's an example. We can pick up an individual P and visualize it, right? So that's the label corresponding, or the P corresponding to label equals 3. We can look at label 35, and it's that one there. We can look at label 36, and it's those two P's there which are each given the same label, which you can also see up here somewhere. There you go. It's those two there, right? Okay, so we don't have a perfect connected components separation of the P's. In fact, there's a big clump of 5 P's here, and a clump of 3 P's there, a clump of 2 there, and a clump of 4 somewhere else. But this is a good starting point, and actually we can figure out ways of separating these p's later on. But a good starting point to get at the average p, so we know what we're looking for on average, is to separate out the single p's. And to do that, we can make use of the area of the p's. So a simple trick is to kind of find what the average area is of a single p, and then look for multiples of that in terms of size of region in order to identify clumps of p's and to eliminate those so that we're left with single p's. And if we do that, we can then assemble our single p's and get a good view of what the average p looks like, and use that for separating p's out by well, there are lots of approaches, some of which we'll go into in chapter 4 and some in chapter 5. Now, this label image that we have here, and also that we have here, gives us a hint to know how many objects have been detected in the scene. And by object, I mean individual p's and multiple groups of p's. And so we have 99 objects in there. Not all of them are p's, and I think there may even be some 1 or 2 stray pixels that still appear, although I can't see any on this image here. There might be 1 or 2 things that are just bits of noise coming from the texture on the desk that might crop in as well. Might not be easily visible here, but I'm pretty sure there's things there that shouldn't be there. And the reason we don't see them is because Matplotlib is doing some smoothing in displaying this. Okay, so now to get the region properties, we can grab this region props routine, which I've already grabbed earlier up, so this is a bit of repetition. But so doing that, regions equals region props, and if we now, so this is what I always do if I am using some module in Python. I always check the type, and so in this case I'm not using a module, I'm using this function called region props out of that module, skimage.measure, and in calling that and giving it the argument of the labeled image, I return the result into regions. I'm just looking at the type of that, and it's just a list, so I can actually run through each element of the list. The number of elements in that list is 99, which matches the biggest value we have in our labels, and therefore we've got one of these regions for each of the one of these elements in the list for each of the regions in the image. So if I look at region 0, for example, then I see that it's something weird of type region properties. And so if I now have a look at what that contains, so dir tells me about the names of variables or elements, attributes that are associated with the that object. And so if I take one of those objects out of the list, then I see that I have these attributes within here. And some of these are, as you would expect, they come out of binary image moments. So in fact, you've got the moments there, the central moments, and so on. You can even have orientation and so on, and some measures of perimeter. So there's lots of things in there that could be very useful. But let's look at area. So if we again look at dir area to see what that is, well, it's got lots of stuff in it, but by looking at it, you can see that it maybe has things that identify it as being a number, so or a numpy type of variable, and if we look at it, we can actually print it, and it's just got a single value, and that, believe it or not, is the number of pixels that is within region 0. So it's one of the p's. And if we do a histogram of the, well, we'll have a look at that later on. So that's the area is just the number of pixels in there. We've also got the bounding box, which you have to be careful with this because these are mn coordinates. So that's the row, that's the column coordinate, that's the height of the bounding box, and that's the width of the bounding box. Okay, so the height and width look pretty big. Look quite different to each other. Actually, I'm just thinking here. Oh no, I'm sorry, that's wrong. So this is the lower row coordinate. This is the upper row coordinate. This is the lower column coordinate. That's the upper column coordinate. Okay, so the bounding box comes back in lower row coordinate, lower column coordinate, upper row coordinate, upper column coordinate for each region in regions. So what we can do is to now do some little sort of graphics to convey this a bit more concisely to us, or to be able to display these bounding boxes. And so what I've done here is to just collect all the bounding boxes in each region. And I'm going to display those bounding boxes using a function called drawRect, which comes out of matplotlib, and it's the .patches module, or the patches module from matplotlib. And you have to be a little bit careful with drawRect, although it's a nifty little routine for drawing rectangles, as you might expect. It uses an XY coordinate system rather than a row column coordinate system. So what I'm doing here is looping over all the bounding boxes once they have been collected, and then calling drawRect with the appropriate bounding box coordinate. So, but this is using an XY coordinate system, or drawRect is using an XY coordinate system. So I swap around BB1, which is the column number for the top left-hand corner, and I make that the X coordinate, and BB0 is the Y coordinate. And then drawRect takes as arguments top left-hand or coordinates of a corner of a rectangle plus the width and the height. And so that's why I'm doing BB3 minus BB1 to get the width, and BB2 minus BB0 to get the height. Okay, so these are operations done for the row coordinate on the column coordinates, and these are the operations on the row coordinates from BB. So that gives us this, which is a box around each of these P's, single P's, or clumps of P's. Okay, so some regions contain multiple P's, as you could also guess by looking at the areas of each of these bounding boxes, or of each of these regions. And so the next step to make sure that we have single P's is to remove the regions that are clumps of P's. Now in practice, you could use some more sophisticated methods to detect individual P's, even at this stage, but you would generally have to do some kind of learning, or to take some sort of initial investigation to understand what the average P looks like, and to be able to make the best decision about where to set thresholds and colors and things like that, and even on sizes. But for the time being, because we have lots of P's, lots of objects, if you like, lots of single objects, then we can just eliminate the clumps of objects and work with the single objects, and that will be a good stepping stone forward, as we'll see. So what I'm doing here is filtering the regions based on their size to remove regions that are too small or too large. So too small to be single P's. I don't know if there are many of those, but definitely we can also remove things that are too large to be multiple P's. So here is a histogram of all of the areas of these 99 objects that we have. And you can see that single P's correspond to this region here, around 750 or so. This corresponds to double P's, and this corresponds to triple P's. Right, so there's only a couple of those in the image. And then there's one that's, I think, 5 P's, which is this one all the way up here. Okay, so by setting a threshold at, let's say, anything greater than 1,000 as a condition for the bounding boxes, or the region sizes, then we can remove those things that correspond to multiple P's. We might also want to get rid of, so you see there are actually some regions that have very, very small size, and those are, if you like, well, they're not P's, they're just bits of noise that have cropped up in the image. So I think we are not seeing, yes, there's one down there, just in there, right? So there's a little region there That's a pixel, and there's a couple. There's one here as well. You can just about see it there, and there's one here. Yep. So note that these don't show up very easily on the labeled image, but they are there, and that again has to do with the fact that the display routine of imshow is not great on Matplotlib. It's not very well written. So there are things that we're not seeing because they're getting smoothed out in the display routine of Matplotlib. Okay, now right. So okay, so this is the filtering operation. So let's just run through that. So that's the filtering. And what we're also doing here is using grabbing the centroid out of the region property as well, and displaying those with red dots, so that we can now see where the centroid of each region is relative to each P, and we can also see where the bounding box is. And now we've got a fairly good selection of single P's that we can group together. Okay, that's just another way of doing that. Okay, now the next step is to grab these P's and kind of create an average P that tells us on average what a single P looks like. Now if we remember that this original image, the color space image, has 3 channels on it. So if we grab subregions around each P, even though each subregion is going to be smaller, we're still going to have a 3-dimensional array representing each P. So if we want to collect these P's and then average them, we need a 4th dimension, which is going to be our experimental space or observation space direction. So in a 4-dimensional space, we can stack these 3-dimensional P regions up. And so this is what's going on here. And now this is a little bit, we have to be careful with this. So if we're stacking things into a 4-dimensional array, one of the problems we have is that each of these P regions at the moment has potentially a slightly different size. And so you can't build a 4-dimensional array or any sort of array if you've got different sizes of subarray. You have to make sure that each of the 3-dimensional arrays that's going into our 4-dimensional array is of exactly the same dimensions. And we don't have to worry about the 3rd dimension, which is the red, green, and blue channels, because that's always going to be the same. But we do have to worry about the width and the height dimensions, because those are different for each P. So there are different ways to handle this, but the way that I suggest is that you find the biggest P that you've got and create a bounding box around that, and then use that bounding box for every other P. In order to do that, you have to make use of the centroid, and then because we're going to resize or potentially grab a bigger section out of all of the P's that we've identified as being single P's, with the exception of the biggest region. So the biggest region will remain the biggest region. All the other regions will go up in size, so that we have one constant size for that extra in those 2 dimensions of width and height. And then once those are all of the same size, we can stick them into the same array, 4-dimensional array, and then average them across that 4th dimension. So this is what's going on here. And so what I've done here is to just make a routine that gets it effectively does a get region from image. And so this is just defining that function, and it's defined in such a way that you pass into this function the image, the centroid, and the width of a square region to be extracted, and it does a check to make sure that that region doesn't extend outside of the image. If it does, then it ignores that region, else it grabs a section from the image of pixels around that region, around the centroid, and returns them. So the return is here, returns the region, and here is the indexing of that region in the color space image. Okay, so first dimension, second dimension, and then the third will be the 3 dimensions of the color space. Okay, so here is the stack of those P's, all now in exactly the same sized array. Okay, so you can see that this is actually a really nice way to look at each individual P. So you can imagine that if people are doing work on microscopy where they're looking at individual cells, this is a really nice way of grabbing individual cells out of an image and then creating a database of cells, if you like. So once we've got this, we can then take this entire 4-dimensional stack of P's and do an average across them across the third axis, which is the observation space, if you like. So it's P space, if you like, and or each instance of P, and average those. And that's what we've done here, where, interestingly, you can see that the imperfections of the P have kind of been averaged out, and you get a really nice looking, yummy, nice full fat P. Okay, so let's just have a quick look through the learning objectives of this particular practical. So first of all, we've seen that in the red, green, blue color space, the original red, green, blue color space, it turns out that we were not able to set a threshold to separate the P's from the background. But by simply mapping into a normalized RGB color space, we're able to set a threshold very nicely. And whilst you can look at the mechanics of that, the important thing to recognize here is a concept, which is that we've mapped the pixel values into an alternative color space. And you can think of that as a sort of a feature space. So it's a demonstration of what you can do with a feature space, whereby things that are difficult to separate in the original measurement space become easier to separate in feature space. And that's exactly what we've seen in moving from RGB space to normalized RGB space. And this is also an explanation of why we have different color spaces in use in image analysis, which is that in some color spaces it becomes easier to separate certain type of structure. Now, if you're a designer, working in different types of color space is sometimes also useful, because it's easier to make adjustments to colors in color space. For example, you may want to just change the hue of something slightly but keep the saturation level similar, or change your intensity but keep the hue the same. And so then a natural color space to use would be hue, saturation, intensity. But similar things exist if you're trying to do image recognition, whereby mapping data from one color space into another, or one type of measurement space into another, makes it easier to do separation of objects or types or classes in that alternative space. Now, I've just spotted a typo here, which I'm just going to fix. Perspective, where's it gone to? Well, I saw it there, now it's disappeared again. Okay, we'll have to leave that. Okay, the other couple of things that we've seen here is learning outcomes. Right, there we go. Right. Okay, so other learning outcome. So you need to be careful with using the histogram routines that are built in to, let's say, Matplotlib. I prefer to use the one, although Matplotlib in principle uses the NumPy histogram routine. The point is you don't have much control over the histogram bins unless you're quite explicit in calling the histogram routine. So if I want to compare two histograms, and the histograms have the arrays that so if I've got two image arrays, or two quantities that I've measured and they're in separate arrays, and I want to do a histogram a comparison of the histograms of those two quantities, then the problem with the histogram routine in general, its default settings, is that it looks for the minimum value and the maximum value in each of the arrays and sets the histogram minimum and maximum values accordingly, and then sets the bins according to that range. So if you want to compare histograms, you have to make sure that the bins that are being used, so the edges of the bins that are being used, are the same for both histograms. Otherwise, it makes no sense to compare the histograms. So the auto scaling or the default options on computing histograms, you have to be very careful with that. And I recommend that you explicitly set the histogram bins themselves, so the bin edges, if you like, or the centers of the bins, so you can control exactly what you're doing, and you can compare histograms in a sensible way. There is some spikiness that we'll see to the histograms. So I haven't talked much about this here, but let's just very quickly look at this conceptually now. So if we look at the normalized red, green, blue values, which are up here, and they're histograms, so not those. Maybe it was the red, green, blue values. Yeah, okay, so here, I didn't have spiky histograms, but if I do this, what I will find with 100 bins, what I find is I will get quite spiky histograms, okay? So in setting 100 bins, what's happening here versus 256 bins? What's happening here is that some bins are capturing 2 intensity levels, and some bins are capturing 3 intensity levels. And so we get this spikiness where the spikes correspond to those bins of the histogram that are capturing 3 integer intensity levels, and the smoother curve underlying it is capturing only results from bins that are capturing 2 intensity levels. So where does that come from? Well, the point is that when we extract the red, green, and blue values, there is usually a precision on how, so there's usually an 8-bit precision on the capture of the red, green, and blue values, which means that even if I were to convert these into floating point values, which I think I've done somewhere, we would still only have integer values present. And that leads to the fact that that leads to the spikiness. So here, some bins are capturing as I say, 2 integer values, and some bins are capturing 3 integer values. So if you have bins back to back to each other, you're going to get this alternating 2 integers, 3 integers, 2 integers, 3 integers being captured inside the bins. And that happens if we set the number of bins to be 100, with the number of pixel values being in the range 0 to 255, and therefore each bin capturing 2.5 units in intensity, right? So fixed width of bin, 2.5 units of intensity, and so we're getting this strange looking artifact. If we increase the number of bins, however, to 256, so we have approximately 1 bin for each intensity level, then that spikiness disappears. Okay. But this is going to depend on the quantization of the data you're looking at, and it's going to be true in any sort of measurement problem where you have finite precision. The number of histogram bins that you set can sometimes lead to this issue with spikiness because of non-uniformity of values with respect to bins. Okay, and then let's just see what else we've got here as learning outcome we need to talk about. Right, so the normalized RGB color space, very easy to do. I've mentioned that already. Okay, connected components labeling. So it gives you the ability to address individual objects in a binary image once you've labeled them. We've looked at how to use properties of binary regions here to get rid of things that don't actually match certain criteria of being a single P. And then we've looked at the idea of creating this observation space and then doing an average across that space to get the average p. So this is similar to what we talked about in chapter 1, where we talked about the idea of the expectation operation. And so if you like, we're looking at the expected p in this example here. Or it's an approximation of the expected p. Okay,